All right, geometry, lesson 60. We're talking about proportionality theorems. Just right on its head, you should kind of get an idea for this. Do we know what proportions are? Do we know how to solve proportions? So basically, the big bulk of this is looking at these scenarios and understanding that whenever I see something that looks like this, I can set up a proportion. And if I can set up a proportion, I know how to solve a proportion, right? So there's really not a whole lot of new solving information here. It's just a new application for something you already know how to solve, right? It's how do I use math that I'm already familiar with to solve problems that I'm unfamiliar with. So previous lessons we've discussed some of the proportional relationships that exist within triangles when they're divided by midsegments. A similar relationship exists for any line that intersects two sides of a triangle and is parallel to one side. So what we've looked at already before is where we have a midsegment and is parallel to the third side, right? And we've seen how that's proportional. What this is saying is that basically eliminate the idea of a midsegment, because a line segment has a beginning and an end, correct? Yes? I can get some heads nodding up and down. We understand what a line segment is. It has a beginning and an end. So in a midsegment of a triangle, it begins and ends on the triangle. With something like this, we're saying that it's the exact same thing as a midsegment. It occurs midpoint between 2 points on a triangle, and it ends, but it cuts through. So it continues to go on. Do you follow me? But it works the exact same way as a midsegment, right? Meaning that it's going to divide the sides of that triangle proportionally. Okay. If a line parallel to one side of a triangle intersects the other two sides, it divides those sides proportionally, right? So we're seeing that XA over AY, so this over that is going to be proportional to this over that. Okay, that's fairly easy. I can set up a proportion. So if I knew that this was, say, 4 and this was 3, and I knew that this was, say, 4 over here, I could set up a proportion of 4 over 3 equals x over 4, right? Cross multiply and divide. I'm probably going to get a decimal number because I'm getting 16 divided by 3. Does this make sense? All right, so we see how that works practically? Okay. All right, the converse. All right, do we understand? I mean, we're not really talking about anything new here. What we're saying is that, let's say I start off with the end in mind, and I should know the beginning, because a converse just merely switches the hypothesis and the conclusion, right? What our original statement said is that if this line is parallel, right, to a third side, then it's going to divide those segments proportionally. What a converse should say then is that if it divides it proportionally, then we know that this line is parallel. Okay, the converse of a triangle proportionality theorem is true. It can be used to check whether a line that intersects two sides of a triangle is parallel to the triangle's base. So we're saying if a line divides two sides of a triangle proportionally, then it's parallel to the third side. We want to remember how converse statements work. Yes, getting heads nodding up and down. So this, what's that? Well, yeah, the question was, it's like a transversal. Yeah, that's not what they're trying to say here, but if these two lines are parallel, then yeah, that red line right there is a transversal to those two parallel lines, which we'd run into stuff from like lesson 12 from that. So we would see that corresponding angles are congruent. Alternate interior angles are, we wouldn't really have alternate interior here, but we would definitely have corresponding angles, meaning that I would know that this angle and this angle are congruent. We'd see this same thing played out over on this side, where that green line is a transversal to those two parallel blue lines, and we'd see that those two lines are congruent. What? Not on this. The question was, can you have vertical angles congruent here? Vertical angles are congruent wherever two lines intersect. We're just not seeing that played out here. Okay? We don't have any vertical. We do have vertical angles. We just aren't solving for them. Okay? It's not working with our proportional parts. Okay? But yes, I mean, this angle right here and that angle right there are vertical angles. They're equal to each other. All right, does everybody follow up to this point? Like I said, I've been 2 weeks out of the classroom teaching, so if I'm talking too quick or if I'm not making sense, please stop me and say, hey, go back, explain that again. Do we understand the proportion into things and how to see that? Okay. Okay, so we can take that and we don't necessarily have to apply it to a triangle per se, but just parallel lines being cut by a transversal in something a little bit more broad like this. And you'll see questions like this show up on things like the ACT. Okay, and so what they're trying to show you is we're using the proportionality theorem. Okay, the triangle proportionality theorem is closely related to what we call theorem 60-3, which uses those same proportion relationships to relate line segments of transversals that are intersected by parallel lines. So we have these lines here that are intersected by a series of parallel lines. Those segments on one side are proportional to the segments that correspond to them on the other side. Okay, so for instance, you see our segment AC here, and we see segment CE. That's going to be proportional to segment BD over DF. Okay? Okay, AC over CE is proportional to BD over DF. So if parallel lines intersect transversals, then they divide the transversals proportionally. So you kind of jumped ahead a little bit, Michael, whenever you're asking about transversals. It does still work with the triangles, but it works for the same reasons that it works here. Okay? All right, if parallel lines divide transversals into congruent segments, then the segments are in a 1-to-1 ratio by theorem 60-3. Any other transversals cut by the same parallel lines are divided into segments that have the same ratio, here 1-to-1. So they'll also be congruent to each other. Okay, we can take this and we can flip it, right? We can reorient it, okay? Yeah, if you're not worried about missing anything. Yeah, there's a video. Okay, so here, if parallel lines cut congruent segments on one transversal, then they cut congruent segments on all transversals. So that's basically saying this, is that if I know that the distance from U to V is 2, and I know the distance from V to W is 2, and I come down here, and I know the distance from X to Y is 3, and I'm wondering, well, then what is YZ? Because these two segments up here are congruent to each other, then these divided segments down here have to be congruent to each other. So what is YZ? What's that? No, well, not necessarily bisect. It would, because it has a 1-to-1 relationship. But what is the distance from Y to Z then? 3. And so you would look at it, and if we set it up as a ratio over here, we'd say 2 over 2 equals 3 over what? Would have to be 3 over 3, because if we simplify 2 over 2, we get 1, right? So 3 over something has to be 1. You cross multiply and find the same thing. Does this make sense so far? Okay? So if you see this question in homework, right, that's a really easy question to answer, but it doesn't mean that people won't get it wrong because they'll forget what the relationship is. Okay? So slow down. I know that I've talked really quickly here. But if V equals VW, then XY has to equal YZ. But could I still use a proportion to solve it if I didn't remember that? Yeah. Okay, so certain things are really nice if you can remember them, then it's automatic. But if you can't remember them, can we still go back to the math? Absolutely. Okay. All right, that's it for that. We only have about 6 minutes just because we chewed up a bit of time. So let's look at lesson 60. Look into your homework, see if there's a question that you want to look at. We can work on answering before we close out. Let's see. Do you guys have number 5? Do you guys have question 5 in your homework? Okay. Let's see. So let's draw that picture up here of 5. It shows you a right triangle kind of reoriented to look something like this. And then we have a line like this that's parallel to this. We're calling this X. We're calling this Y. Those are just points. This is point P. This is R. This is Q. We know that this is 6. It's a really funky 6, but it's fine. We know that this is 4. All right. The question shows you, it says in triangle PQR, angle P is a right angle. Find the perimeter of this to the nearest tenth. So a couple of things that we need to do, because we want to find perimeter, which means the distance all the way around, correct? Okay. So notice that it is a right triangle, so at some point I should be thinking about what? Using what? Pythagorean theorem. But so far, do I know what the distance of PQ is? No. Do I know the distance of PR? Yeah, we know that that's 9. Okay, but that's not enough to solve the Pythagorean theorem. I need to know first what that is, right? Perfect. 5 over 4 is equal to x over 6. So that's going to solve for that length. What? 30 divided by 4, good. What is that? 7.5. So what do I want to do with this 7.5 over here? Add it to 6, good. Right, we're going to need RQ. What did we say PR was? What? 9. Okay, so we know the length, that side is 9. What is PQ? 13.5. How do I use 9 and 13.5? Yes, good. He just asked if RQ was the hypotenuse. Yes, it is, because it is where? No, not because it's at the bottom, because it's opposite the right angle. Very good. All right. 13.5 squared equals, what we would say is RQ squared if we wanted to, something like that, or X squared. 9 squared is what, 81? 13.5 squared is, it's over 169. 182.25 equals RQ squared, and if I was in this class, right, I would want to be writing down this work because that's going to save me from needing to do question number 455 on my own. 263.25 is what we get when we add those up, is RQ squared. Okay, we want just the square root of that though, right? All right, we got 16.22 for my answer. I need to do one more thing. What is that? My answer is not 16.22 because I need to go back and see what was the actual question. Find the perimeter, right? We needed RQ to find the perimeter, but now what do I need to do? Add up all the whole sides. So 9 plus 13.5 plus 16.22. What is my perimeter? All right, and we're going to take it to the nearest tenth. So 38.7. And they didn't give me any kind of units, I don't think. So we're just going to leave it like that there. All right, do we feel like we have a basic understanding? I know we covered that in like 10 minutes, it feels like. But hopefully that's enough to kind of get some help.